Hello everybody, this is Dr. Christopher White and welcome to part 3 of Geologic Time. So we've been talking about radioactive isotopes, but now we need to think about, well, why are some isotopes stable and other isotopes unstable? So radioactive decay can be caused by an imbalance in the forces holding the nucleus together. So I'm sure you remember a nucleus of an atom or an isotope consists of protons and neutrons, and the electrons orbit around that nucleus. So if there's something wrong in terms of the equilibrium within a nucleus, it's naturally going to be unstable. So there's a few reasons why your nucleus can be unstable. So the first possibility is it's an imbalance in the forces. So let's talk about that problem first. So your nucleus is held together by a force called the strong nuclear force. Now the strong nuclear force is a very powerful force, but it only works over very, very, very small distances, tiny distances. So how powerful is the strong nuclear force? Okay, so if you imagine we have our nucleus and we have two protons. Now protons are positive. So you would assume that as you move protons towards each other, because they're both positive, they're going to naturally want to repel each other. And you would be correct in that assumption. However, when you manage to get these two protons close enough to each other, the strong nuclear force kicks in. And so the strong nuclear force is actually so powerful that it can overcome the repulsion between the two protons. So the strong nuclear force is actually what's sticking your nucleus together and holding all those protons and neutrons to form a solid nucleus. Now, there's another force which is operating in the opposite direction to the strong nuclear force. So that's the electromagnetic force. So the electromagnetic force is that repulsive force between the protons. Okay. Now, under normal conditions, the strong nuclear force is powerful enough to overcome the electromagnetic force. However, if your nucleus gets too large, well, unfortunately, the strong nuclear force is not powerful enough. Now, so the strong nuclear force has essentially a limit to its radius, how far the strong nuclear force can extend. So this means that if you have a very, very large nucleus, the strong nuclear force will not be that strong, especially along the margins of the nucleus. Now this means that when the strong nuclear force is weakened, it means the electromagnetic force can become dominant over the strong nuclear force. And if that happens, well then the repulsive forces between the protons are going to start pushing the protons away from each other. And obviously at that point, your nucleus is going to start to want to rip itself to pieces. So how does your nucleus stop this happening? Well, the most straightforward way is an alpha decay. So in the case of an alpha decay, your nucleus simply goes, right, okay, I'm too big, I've got to lose some weight. And so the nucleus goes, right, I'm just going to get rid of two protons and two neutrons. I'm going to throw away an alpha particle. So that's an attempt to get rid of protons and neutrons, and in the process, that's going to make the nucleus smaller. And by making the nucleus smaller, it's going to make the strong nuclear force more powerful. And hopefully, by getting rid of protons and neutrons, you will get to the point where the strong nuclear force is able to become stronger than the electromagnetic force. And when that happens, your nucleus will be stable and it will no longer want to tear itself to pieces. So an imbalance in the forces, so the strong nuclear force and the electromagnetic force, is typically due to very large nuclei. And very large nuclei will often try and achieve balance through alpha decay by getting rid of material. So that's problem number one and how to solve it. The other possibility is the number of protons and neutrons. Oh, I should point out, I do apologize, should have read this. Anything that's larger than bismuth, so any element larger than bismuth will have a nuclei that's so large it will naturally undergo alpha decay. So bismuth is actually 83 on the proton number, so it's going to be just to the right of this dashed line here. So you'll notice that everything above bismuth, or a lot of them anyway, a lot of these isotopes are marked out here in yellow. And that means they will naturally undergo alpha decay. Okay. Now, the other reason that your nucleus can be unstable is because there's an imbalance in the proton to neutron ratio. So Isotopes may be unstable due to the number of protons and neutrons in that nucleus. So you have these things called magic numbers, and a magic number is a certain number of protons and neutrons. There are some nuclei that are, well, there are some numbers of protons and neutrons in the nuclei that are just naturally stable. So if you have, let's say the correct number of protons, so you have one of these magic numbers, let's say a magic number is like 8 protons. So if you happen to have an isotope that has 8 protons in its nucleus, it's naturally going to make that nucleus more stable and therefore less likely to decay. So if you have a nucleus that contains magic numbers of protons and neutrons, then it's naturally going to be stable. So most stable nuclei have even numbers of protons and neutrons. So if we look at this table here, we can see these are stable isotopes. So you can see these are the number of stable isotopes: 157, 53, 50, and 5. So what we're going to look at is we're going to look at the numbers of protons and neutrons. So you'll notice that the most stable isotopes have even numbers of protons and neutrons. And so having an even number of either protons and neutrons is a good thing in terms of stability. So when you have even numbers of both, it's an excellent thing in terms of stability. So most stable isotopes have even numbers of protons and neutrons. The second option is that you have an even number of protons but an odd number of neutrons. So although it's not as effective as having even numbers of both, you still see it's still good. So having an even number of protons is a good thing. Same thing with having an even number of neutrons. So even if the number of protons is odd, an even number of neutrons will still be more likely to produce a stable isotope. Now down here at the bottom we have odd numbers of protons and neutrons, and you'll notice that the number of stable isotopes with both odd numbers of protons and neutrons is extremely low. So nature does not like odd numbers of protons and neutrons in the nucleus. So if you have a nucleus that has odd numbers of protons and neutrons, it is more likely to naturally be unstable, and therefore it is more likely to break down through radioactive decay. So isotopes will have these preferred ratios of protons and neutrons. So it's not only is the number of protons and neutrons even, it's also a question of what's the ratio between them. So elements containing up to 20 protons, so 20 protons is calcium, will have a proton to neutron ratio of about 1 to 1. Okay, so for every 1 proton you have 1 neutron. And that's good, that's what they need to achieve balance. When you go above 20, so that's scandium, all the way up to bismuth, which is 83 protons, the ratio is 1 proton to every 1.5 neutrons. So you need more neutrons than protons in order to achieve balance. Anything that has a proton number in excess of 84 is unstable, because we discussed in the previous slides that a nucleus which is too large is naturally going to be unstable due to problems with the strong nuclear force electromagnetic force balance. So in order to try and achieve balance for the proton-neutron ratio, well, the most straightforward way to do that is through either beta decay or electron capture. So if you have the wrong number of protons, you simply take a proton and turn it into a neutron. If you have the wrong number of neutrons, you take a neutron and you turn it into a proton. And so all you've got to do is keep changing the numbers of protons and neutrons until you eventually manage to achieve a stable configuration. So that's the reason behind beta decay and electron capture. It's nothing to do with the size of the nucleus and the strong nuclear force and electromagnetic force. When it comes to beta decay and electron capture, it's more down to this proton-neutron ratio and your isotope trying its best to achieve a nice stable configuration. So unstable nuclei will continue to decay until a stable configuration is achieved. So if you remember, our unstable nuclei is called the parent isotope, and the stable isotope that it eventually manages to reach is called the daughter isotope. So in the case of uranium-235 here, it will decay to the stable isotope, which is lead-207. So uranium-235 is the parent isotope, lead-207 is the daughter isotope. So the thing you'll notice is it doesn't go directly from uranium-235 to lead-207. There are all these intermediate stages, aren't there? So this is called a decay chain. And as you can see, so uranium's going to decay via alpha decay. It's going to turn into thorium. So it's kicked out 2 protons and 2 neutrons. So it's gotten rid of some protons and neutrons to try and make itself smaller. That's that's trying to achieve balance. Now, once you change the number of protons and neutrons, your nucleus is going to have to try and rebalance that proton-neutron ratio. So your thorium nucleus is going to undergo beta decay, so it's going to take one of the neutrons and turn it into a proton, in which case we now end up with protactinium. So then that's going to undergo alpha decay and come down here to actinium. So that's then going to have to rebalance itself, because now we've changed the numbers of protons and neutrons. It's going to undergo beta decay again, so a neutron will turn into a proton, etc. So it's got to go through all of these stages in an attempt to try and achieve a stable configuration. And it doesn't always, well, should I say practically never, parent isotope straight to daughter isotope. There are normally several intermediate isotopes before you manage to make it to the stable daughter isotope. And this, of course, is called a decay chain. Now, the most important thing is in a second we're going to talk about half-lives. And a half-life is, in order for a half-life, you have to have what's called a complete decay. So your uranium-235 has to have fully decayed to lead-207. So let's talk about half-lives. So a half-life is defined as the amount of time required for 50% of a radioactive isotope, so that's the parent isotope, in a given sample to fully decay to a stable daughter isotope. Please note, that is fully decay. So it's not 50% of the uranium makes it halfway along the decay chain. It's 50% of the uranium has to have completely made it to the stable daughter isotope. So half-lives range in length. They can be anywhere from billionths of a second, so hydrogen-7 has a half-life of about a billionth of a second, to 2 septillion years in the case of tellurium-120. Now, radioactive decay is not a uniform change. So what do I mean by uniform change? Well, think of you're putting a drop of water into a glass. So every time you put a drop of water into the glass, the level of water in the glass is going to rise up by the same amount each time, isn't it? You're not going to get that with half-lives. And I'm going to show you a graph in a second, which is going to show you what's going on. Now, the most important thing about half-lives and radioactive decay as a whole is that it's a constant. So the parent isotope is decaying to the daughter isotope at a set rate. So that means if we can take a crystal, so let's say a crystal of a mineral like zircon, and we can measure how much daughter isotope there is in that crystal of zircon, and we can calculate how much of the parent isotope the crystal started with, well, as long as we know how much of the parent isotope the crystal started with, and how much of the parent isotope is left when we measure the crystal, well, then we can very quickly work out exactly how long it would have taken to get from the starting concentration of the parent isotope to the concentration of the parent isotope that we can measure now. And the only reason we can do that is because radioactive decay is a constant. It's like a second hand on a clock. It's constantly occurring at a set rate. So we have a couple of different ways of looking at half-life. So let's look at the table over here to start with. So this table has 4 columns. So the half-life, so that's the amount of the parent isotope remaining. So here in the percent, this is how much parent isotope remains in the sample after every half-life. So as you can see, at half-life 1, our sample contains 100%, sorry, half-life 0, sorry, our sample contains 100% parent isotope. So we're starting off with 1 million isotopes of the parent isotope, and obviously because no decay has happened yet, we have 0 daughter isotopes. After 1 half-life, 50% of the parent isotope has changed from the parent to the daughter, completely. After 2 half-lives, well, that's half of this number has now turned into the daughter isotope. So now, as you can see, the parent isotope has decreased by half from the previous amount, whereas the number of the daughter isotopes has now increased by 250,000. So what you're going to notice is the amount of parent isotope each time is going to decrease by half, and obviously the remainder is going to be added to the daughter isotope column. The most important thing to think about is that we're not actually losing anything. So if you take a second and you start adding up all these numbers, what you're going to notice is you always end up with 1 million isotopes. Because all we're doing is we're taking parent isotopes and turning them into daughter isotopes. We're not actually losing anything. So the numbers of parent and daughter isotopes never change. It's just simply the ratio between them will change over time. So every half-life we lose essentially half of the previous amount of the radioactive parent isotope. So if we look at this graph over here, we have the same situation. So here's our mineral, and in our mineral we have 100 isotopes of our radioactive parent. Okay, obviously because no decay has taken place yet, we have 0 daughter isotopes. After one half-life, we go from here to here. So this is essentially 50% of the parent isotope turns into the daughter isotope. So now we have 50 atoms of the parent isotope and 50 atoms of the daughter isotope. From half-life 1 to half-life 2, the amount of the parent isotope halves again. So by half-life 2 we have 25 atoms of the parent isotope and 75 atoms of the daughter isotope. From half-life 2 to half-life 3, the amount of parent isotope halves again. So now we have 13 atoms of the parent isotope and 87 atoms of the daughter isotope. From half-life 3 to half-life 4, the amount of parent isotope halves again, so we now have 6 atoms of the parent isotope and 94 atoms of the daughter isotope. So every time we go from one half-life to another, the amount of the parent isotope is divided by 2. Now, the most important thing to remember is that the amount of time it takes you to get from half-life 0 to half-life 1, and from half-life 1 to half-life 2 is the same. So let's just say for argument's sake it takes, the half-life is 100 million years. So it's going to take you 100 million years to get from here to here. It's also going to take you 100 million years to get from half-life 1 to half-life 2. It's going to take 100 million years to get from half-life 2 to half-life 3, and it's going to take another 100 million years to get from half-life 3 to half-life 4. Because radioactive decay is a constant. The rate doesn't change. It doesn't matter how many isotopes of the parents you have, the rate of decay is still always going to be the same. So once again, as long as we know the amount of the parent isotope we start with in our mineral, and we know the amount of parent isotope we have left over when we actually measure the crystal, well, all we have to do is we just have to work out exactly how long it will have taken, the amount of parent, it would have taken, how long will it take for the parent isotope to break down to give us, the amount of parent isotope that we have now. That was an absolutely horrendous explanation, wasn't it? And I do apologise. But the most important thing is as long as we know how much parent isotope we start with, and how much parent isotope we have left when we actually measure the crystal, we can work out very, very easily how long it will take us to get from the amount that we start with to the amount that we see when we actually analyse the crystal. And we can do that because the radioactive decay is a constant. So if we look at half-lives, you'll notice very, very quickly that half-lives are not the same. So depending on what's actually decaying, the half-life will vary. So here we have 5 of the most common half-lives used in geology when it comes to dating rocks. So we have uranium-238, uranium-235, thorium-232, rubidium-87 and potassium-40. So you'll notice that for uranium-238, the half-life is about 4.5 billion years. So that means that over half of the original uranium-238 that was in the Earth when it first formed has now decayed to lead-206, because of course the Earth is 4.56 billion years old. In the case of uranium-235, the half-life is 700 million years. In the case of thorium-232, the half-life is 14 billion years. So, the universe is very quickly moving to being 14 billion years old. So, we're pretty close to, all the thorium in the universe, or the thorium-232 in the universe achieving its first half-life. So, rubidium-87 has a half-life of nearly 49 billion years. That's a pretty big one. And potassium-40 has a half-life of around 1.3 billion years, quite, another long half-life. But the most important thing is the half-life doesn't change. It doesn't matter how many parent isotopes you have, the half-life is a constant. So next question is well, what minerals do we want to use when dating a rock? Now remember, we can use the minerals to date the rock because the minerals are part of the rock. So that means when the mineral crystallized, well, that's part of the rock forming process, isn't it? So that crystal is considered to be part of the rock, and therefore we can use it to date the rock as a whole. So what we want is we want a mineral that will allow in the radioactive parent isotope into the crystal lattice, but not the daughter isotope. So if we are going to try and, let's say, date a mineral using uranium-238, that's going to be what we're going to use to date our mineral. Well, what we want is we want the mineral that we're going to use to date our rock. We want that mineral to let uranium into the crystal lattice of the mineral when it's forming, but not lead. So that means when our crystal first forms, it will have some uranium in it, but it will have no lead. Now that means, let's say, when we come along in, I don't know, 4.5 billion years, we will therefore know that any lead that we detect in that crystal is exclusively due to radioactive decay, because there was no lead there in the first place. Okay, so that's very important. Our mineral has to let in the radioactive parent isotope, but it doesn't let in the daughter isotope. So that means when our crystal first forms, it has no daughter isotope in the crystal lattice. Okay, so if we're using a crystal of zircon, zircon will let uranium into the crystal lattice, but it will not let lead into the crystal lattice. So that means when we come along and we measure our crystal of zircon, any lead that we find must have come from radioactive decay. It's the only way it could get there. So yeah, the classic example is the crystal zircon. So zircon contains the element zirconium, and it just so happens that zirconium can substitute with uranium very, very easily. So as your zircon crystal grows, some of the zirconium will be replaced by uranium. So that means as your zircon crystal is forming, it will let in small amounts of uranium into the crystal lattice. However, lead cannot substitute for zirconium. It's the wrong valence and it's the wrong size. And so this means that when your crystal of zircon is growing, it will not let in lead. So when your crystal of zircon is all shiny and new, it means it will contain a small amount of uranium within it, but it will contain 0 lead. Okay, and that's very important, because when we come along in however many million years and we analyse the crystal, well, all we've got to do then is we simply measure the amount of uranium, we measure the amount of lead, and then we add those two numbers together. And that gives us the amount of uranium we started with, doesn't it? Because think about it. Radioactive decay, all we've done is we've taken uranium and turned it into lead. That's all that's happened. So if we add the amount of uranium we have when we actually analyse the crystal, and we add the amount of lead we have when we analyse the crystal, add those two numbers together, that tells us how much uranium we actually started with. And so in that case, we now know the amount of uranium we started with. We know how much uranium is left in the zircon crystal when we analyse it. So all we have to do is just calculate how long it would take you to get from stage 1 to stage 2. That's all it is. And as you can, it's actually relatively basic math. It's not that complicated. So is there anything else we want when we're trying to find a good mineral for radiometric dating? Well, yeah, one of the most obvious ones is we would love it if the mineral we're looking at is common. The more common it is, the easier it's going to be to find, and the more of it there's going to be. And so that means you can analyze your rock more efficiently and more cheaply. If you have a situation where the mineral you're trying to date, is only an absolutely tiny proportion of the rock you're analysing, well, then you're going to have to get, a huge sample of the rock. You're going to have to, process it, which is going to, take up time and money, and you're only going to get a few crystals to actually analyse at the end. On the other hand, if the mineral you're using is really, really common, well then you don't need that much rock, and you're going to get loads of crystals which you can use for analysis once you've processed it, and it's going to be done faster and more cheaply. So a common mineral is helpful, and zircon is a great example of that because zircon is a very common mineral. It's also helpful that your mineral is resistant to chemical alteration or weathering. So we want our crystal to be stable. So this means that over time our crystal won't be damaged by chemical processes or physical processes. And so this means the crystal that we analyze in the lab will be the crystal that pretty much formed when it crystallized out from, let's say, the magma. Okay, it will be, nothing will have changed because we want our crystal to be a closed system. The final thing we want is something which is called a high closure temperature. So a high closure temperature simply says if I take my crystal of the mineral I'm analyzing, there's a magic temperature, and if you go above that magic temperature, your crystal can start to lose parent and daughter isotopes. Okay, so if you get the temperature high enough, the crystal lattice of your crystal will actually begin to weaken a little bit, and that will allow parent and daughter isotopes to actually leave the crystal. So you're losing material, you're losing parent and daughter isotopes. Remember, radiometric dating requires your crystal to be a closed system. It means you can't lose parent or daughter isotopes. But if you go above that closure temperature, well then we start losing our parent and daughter isotopes. So then our crystal is no longer a closed system, and we can't really use it for dating our rocks. So what we want is a crystal that has a very, very high closure temperature, because the higher the closure temperature, the less likely it is that you will be able to reach that temperature. So the crystal will be highly unlikely to have lost parent or daughter isotopes. So yeah, there are uncertainties though when we are dealing with these minerals, and the process I was just describing is called leakage or loss. And this is the process by which your crystal is taken above its closure temperature, and this allows parent isotopes and or daughter isotopes to exit the crystal. So in the case of zircon, for instance, so if I have a crystal of zircon, we've already gone and discussed how uranium is perfectly okay substituting for zirconium. However, lead does not substitute for zirconium. So the problem is, if you have a zircon crystal and some of the uranium has decayed to lead, well, the zircon crystal isn't really going to want that lead in the crystal, is it? So if you manage to take that zircon crystal above its closure temperature, it's going to naturally kick out that lead because it doesn't want it. And so this would be a case of leakage. We are essentially losing, in that instance, the daughter isotope, and so that means we no longer have a closed system. So closure temperatures vary between minerals. So for something like a mica mineral like biotite, your closure temperature is going to be about 350 Celsius. So from a geologic point of view, at least quite low. In the case of zircon, the closure temperature is in excess of 1000 degrees Celsius. So zircon is an absolutely wonderful crystal because it has this huge, but pretty darn high closure temperature. And so that means it's very difficult for your zircon crystal to be reset and suffer leakage. So if we lose the daughter isotope from our crystal, that's going to lead to an age which is too young. If we lose the parent isotope from our crystal, that's going to lead to an age which is too old. So one of the ways we get around this problem is we actually assume that the outsides of the crystal that we're analysing have suffered loss, even if it hasn't. We work under the assumption that the crystal has actually suffered some loss along the edges of the crystal. And so what we do is we actually physically or chemically abrade away this outer edge of the crystal. So we actually dissolve it and get rid of it. And this means all we're left with is the center of our crystal, the core of the crystal. And that is what we actually analyze. And that's how we try and get around this problem of leakage. And so this diagram here kind of summarizes the problem. So here's our crystal. Now let's, for argument's sake, say this is zircon. Okay, and these big blue circles represent the uranium. As we've discussed, the uranium is perfectly comfortable in the zircon crystal lattice. Now, over time, some of this uranium is going to decay to lead, which are the small blue circles. The problem is the lead is not welcome in the crystal lattice. Now, what happens is if we were to take our zircon crystal and take its temperature above 1000 degrees Celsius, well, at that point, all of a sudden, the crystal lattice of the zircon crystal is going to become a little bit flexible. And so what will happen is the zircon crystal will kick out the lead because it doesn't want it there. And so you can see your crystal at this point is undergoing leakage. And then when you come along later on, you actually analyze your crystal, well, that means you're going to get an age of your crystal which is too young. Okay, so leakage is a bit of a problem. It does have one useful point though. We can actually, if we are careful, we can actually work out when this resetting took place. So we can actually use it to date rocks, or more accurately, date the time when a rock has been metamorphosed. So that is the one thing that leakage is useful for. The problem is, in order to get this information, you obviously have to destroy the earlier crystals, or should I say reset the earlier crystals, which is something you really don't want to do. So what can we date using parent-daughter ratios, excluding carbon? Well, there's a whole range of stuff we can date. So we can date meteorites. You know, how do we know the Earth is 4.56 billion years? The answer is we took some meteorites and we dated them. And we used samarium-neodymium and rubidium-strontium to date meteorites. In terms of igneous rocks, now igneous rocks are the main type of rock which is actually dated. So, because it just so happens they tend to have quite a lot of zircon in them, for instance. Igneous rocks, they can be dated by uranium-lead dating, samarium-neodymium, rubidium-strontium, or even potassium-argon. So there's loads of ways you can date igneous rocks. The most common way is uranium-lead dating, simply because zircon is so common. We then have sedimentary rocks. Now, sedimentary rocks are extremely difficult to date using radiometric methods. The problem is that if you think about it, a clastic sedimentary rock is made up of pieces of other rock. So when we date the sandstone, we're not dating when the sandstone formed, we're getting a date for when the rock that was eroded to make the sandstone went and formed. So this means that clastic sedimentary rocks are very, very difficult to date using radiometric methods. You can use potassium-argon dating on a mineral called glauconite, and you can use uranium-thorium dating on ocean sediments, particularly those that contain carbonate minerals. However, they are very fiddly techniques, and they're very expensive. So it's not easy to do. And when it comes down to it, sedimentary rocks are actually relatively easy to date because lots of sedimentary rocks contain fossils. And so, why waste, thousands of dollars, trying to date a rock radiometrically when you can just look at the fossils and that will tell you, the age of the rock anyway. Now, metamorphic rocks, as we just discussed, we can date when metamorphism took place using the timing of leakage. So we can use that to our advantage. But in terms of actually any other technique, no, we can't really, use the primary crystals to date when the formation of a metamorphic rock. We need to try and use the leakage to try and time when that metamorphism actually occurred. So it should be noted that only zircon and badleite, so badleite is another zirconium mineral, so zircon is zirconium silicate, badleite is zirconium oxide, and techniques that use rubidium-strontium. Those are the only two techniques that have high closure temperatures. And so by their very nature, they're considered to be the most reliable because it's very difficult to reset those particular radiometric decay chains. Okay, so do you know what? I have been going on for a very long time, so this is probably a good place to stop the presentation. So once again, pause the video, well, stop the video, should I say, get up, have a walk around, get a glass of water, a cup of tea, sit down, take a few minutes, and then come back for the fourth and final part.